Okay, I just wanted to work through one more example together. So I've chosen another even numbered problem from your book. This is number 24. If you want to pause the video and try the problem on your own, I would really encourage you to do that and then just come back in and check in. If you want, you can even just fast forward to the answer and see if your work was right, or you can watch the entire thing and work through it together with me. Okay. So we're given this integral. We're integrating over r, x plus y, e to the x squared minus y squared with respect to area. And r is the region that's bounded by these four lines. X minus y is 0, x minus y is 2, x plus y is 0, and x plus y is 3. Okay. Now I can certainly draw the region R if I want to, but notice I don't actually even have to in order to figure out what region I want to be working with in the UV plane. Because if I simply set u equal to x minus y, u is varying from 0 to 2. And if I simply let v equal x plus y, v is varying from 0 to 3, I've got this lovely rectangle in the xy plane. So having these equations where the same thing is constant in a pair of equations really gives me a strong suggestion of what I would want u and v to be. Okay. Now, of course, I could actually graph r. I'm going to, just so I don't feel too lazy. This would be x equals y. This would be y equals x minus 2. So it's this line like this. This is y equals negative x. And this is y equals negative x plus 3. So we're talking about this diamond-shaped region here. It's not an atrocious region, but I like the rectangle better because I've got nice limits of integration. And here, this is neither type 1 nor type 2 because the top boundary and the bottom boundary change, as do the left and right boundaries. So if I were to work in this system, I'd have to chop this up into two separate integrals. I can also see it looks like my integrand is going to become a whole lot nicer. So I'm just going to say, okay, let's integrate over s. So from 0 to 2, from 0 to 3. Notice x plus y, that's just v. E to the x squared minus y squared is x minus y times x plus y. That's just e to the u times v. Now I'm going to have my scaling factor, which is going to be the absolute value of the Jacobian. And then, let's see, the way I've set it up is du dv. I want to take a look at that and see which one I want to actually do first. Actually, I like that. Because here I'm thinking I want to do a w substitution. So I would let w equal u times v. If I'm integrating with respect to u, I have the v that I need to be able to do that. Okay. But here's a situation, notice, where I've got constant limits of integration, but because of the integrand, one order of integration is going to be a lot simpler than the other. In this case, I just sort of blindly wrote it out, and I lucked out that I got the right one. Had I not, I would have immediately said, no, let's Frobenius. Okay, fabulous. So I know what goes here is the absolute value of my Jacobian, del xy by del uv. Okay, so I need to get x and y in terms of u and v. Now, I think I mentioned that there was a way that I could keep it in terms of this and find the Jacobian of this, the inverse transformation. I misremembered that there was a homework problem in the book that worked through that trick. I was thinking of our old textbook. There is a way to do that. I'm happy to talk about it with folks in office hours. You're welcome to look it up, but you're not going to find it in the homework for this section. So I apologize for leading you astray, but that's something I just do from time to time. All right, so if I'm trying to solve for x and y in terms of u and v, if I just add these, I get 2x equals u plus v. So x is u plus v over 2. And I'm just going to write that as u over 2 plus v over 2. Okay. Now, if I wanted to solve for y, y is v minus x. So that's v minus u over 2 minus v over 2. A whole v minus a half of a v is the other half of the v. So I get v over 2 minus u over 2. Okay. So my Jacobian, del xy, del uv, is the determinant partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v, which is going to be the determinant. Let's see. This was x. Partial of x with respect to u is a half. Partial of x with respect to v is a half. This was y. Partial of y with respect to u was a half. Partial of y with respect to v is a half. Sorry, I meant to say a negative 1/2 right here. So when I calculate this, I'm going to get 1/4 minus a negative, so plus a fourth. That's 2/4 or 1/2. Now I want to take the absolute value of that, and the absolute value of a half is a half. Okay. Yes, I believe you can do that in your head. I like to write it down just so I don't forget, because it's so easy if you do 3 problems in a row where your Jacobian is positive, so you don't bother to take the absolute value. It's so easy to forget it when on the 4th problem you get a negative Jacobian and the absolute value is necessary. Okay, so my scaling factor here, is just 1/2, and now we can integrate. So, I said I was going to want to do a w substitution. I'm going to let w equal uv, and I'm integrating first with respect to u. So my dw will be the partial of this with respect to u, which is just v du. Okay. So that v is going to get absorbed into my dw. So we're integrating from 0 to 3, from 0 to 2v. These were my u values, so my w value is going to be that times v. Okay. And what we're integrating is e to the w dw, and then we'll have to integrate that dv. So integral from 0 to 3, antiderivative is just e to the w, and we're evaluating that between 2v and 0, and then we'll integrate dv. So that's the integral from 0 to 3, e to the 2v, minus e to the 0 is 1. So don't get in the habit of saying, oh, I'm plugging in 0, it just goes away, because it doesn't. dv. All right, that's the integral from 0 to 3 of e to the 2v dv minus the integral from 0 to 3 of 1 dv. That's a quick u sub. If you're comfortable doing the u sub in your head, I'm totally fine with that. I'm actually feeling tired today. I don't trust myself to do mental math. So I'm going to say, let's see, we've used u, v, and w, and x and y. Let's say z. We'll do a z sub. Let's let z equal 2v. So dz is 2 dv. So I introduce a 2 and a 1/2. All right. So then that becomes 1/2 the integral from 0 to 6. My limits of integration change. E to the z dz minus, this is just going to be 1 times the length of that interval, which is 3. So that's 1/2 e to the z evaluated between 6 and 0 minus 3. So that is 1/2 of e to the 6th minus 1, because that's e to the 0, minus 3. So that's half of e to the 6th minus a half, minus 3 is just minus a total of 7/2. And that is our lovely integral.